Welcome to the NanoDim mini class. Today we'll be discussing pulmonary hypertension, a condition caused by various factors and mechanisms that lead to hemodynamic disorders and pose a significant threat to human health. Recently, Junyi Hu, Guowei Tu, Shenhui Liu, and Xiaodan Zhang have made remarkable contributions to the treatment of pulmonary hypertension.
That sounds amazing. The study analyzed the structural state of endothelin receptors bound to antagonists, providing an important new approach for developing targeted drugs for pulmonary hypertension. Could you explain in simple terms what endothelin and receptor antagonists are?
Yes. So endothelin is a hormone that, when binding to endothelin receptor A, acts on vascular smooth muscle cells, causing the muscles to contract, which narrows the blood vessels and increases blood pressure. Antagonist receptors can also bind to ETA but do not produce an effect. By occupying ETA without activating it, the antagonists significantly reduce the number of receptors available for endothelin binding. This prevents the smooth muscle from contracting, thereby lowering blood pressure.
It's an interesting mechanic. Can you tell us what the research team found specifically?
Through high-resolution electron microscopy analysis, the team identified several key residues that contribute to the selectivity of endothelin receptor antagonists, such as R326.6.55, K116.3.33, and W319.6.48. These residues play a crucial role in the binding process between the receptor and antagonists, influencing the drug's binding affinity and selectivity. Notably, the study reveals that the second extracellular loop of the endothelin ETA can serve as an epitope for antibody-mediated receptor antagonism.
Does this mean that by designing a specific antibody against ECL2, can effective antagonism against the ETA receptor be achieved?
Exactly. This discovery not only broadens our understanding of endothelin receptor function, but also offers a new approach for developing therapeutic strategies.
The details of the protein mechanism must be in high resolution to be read, right?
Yes. The team used the China-made alloy grid named ANTcryo, which covered with nickel titanium film, and finally collect the high-resolution electron microscopy pictures in 3.0 angstrom.
Why can the ANTcryo grid provides the higher resolution than other grids do?
First, ANTcryo is conductive, which effectively reduces beam-induced motion. Second, the surface of the antefilm has minimal nonspecific adsorption forces, promoting a more uniform distribution of samples within the holes. Finally, the surface of the antefilm is hydrophilic, offering good surface properties and biocompatibility, all of which help enhance imaging stability and resolution.
Seems ANTcryo is a good helper to the research team. Do you think that ANTcryo will have a bigger market?
Yes, ANTcryo also improves sample preparation success rates and saves electron microscope time. Research teams working on complex proteins should consider trying this grid, as it will surely provide a better sample preparation experience.
If you want to try some, just scan the code and contact us.